Canada is a tier 1 nuclear nation, home to one of the world's most innovative nuclear power reactors known as the CANDU, or the Canadian Deuterium Nuclear Reactor. As the world looks towards combating climate change and reducing its emissions, nuclear technologies present a really good opportunity to both advance humanity and mitigate the effects of climate change. That's why in this video, I'll be doing a technical deep dive into the CANDU reactor and explaining exactly how this nuclear power reactor works. I'll be going through everything you need to know about this CANDU reactor design, which is pressure tubes, heavy water, how it takes natural uranium fuel and converts that into electricity end to end. Hey friends, my name is Osama. I have a background in nuclear engineering, and on this channel, I help demystify nuclear technologies by simplifying them. I also make educational resources on all things related to the CANDU nuclear reactor as well. Let's start with the Calandria, which is the heart of the CANDU reactor. It's the reactor vessel which holds the fuel and pressure tubes in this reactor. Imagine a large tank the shape of a tin can, but this tin can is placed sideways. That's how a Calandria looks like. And it's also filled with heavy water. Most nuclear reactors across the world have a single pressurized vessel. And what's different about the CANDU reactor is that instead of having one single pressurized vessel, it has hundreds of pressurized tubes that are held together by the Calandria. Depending on the energy capacity, there are around 380 to 480 of these pressurized tubes in a Calandria. Since these pressure tubes play such an important role in the CANDU reactor, let's do a bit of a technical deep dive into the technology. Now let's start with the pressure tube, which holds the fuel in the nuclear reactor, is actually surrounded by another tube called the Calandria Tube. Now these two tubes are really important as they are called the fuel channel. The main action takes place in these pressure tubes, which hold a total of 12 fuel bundles each. Once this heavy water flows through the pressure tubes, it's then directed to the primary heat transport system, which job is to, like I said, transport heat from the reactor core all the way to large steam generators. Now these steam generators are heat exchangers which use the heat to create steam, and then the steam is spent off to turbines which spin and create electricity. Pretty simple. So what about the second tube that surrounds the pressure tube, the Calandria Tube? Well, it plays a really important role since it holds the heavy water moderator. The moderator in the Calandria Tube is a really important part of a nuclear reaction, and the reason why is because the moderator is a way to control the reaction. The moderator plays a really important role also as a backup safety system in which you can release a liquid chemical which can stop the reaction in its tracks. So you have control rods which also play a role in stopping the reaction as a primary mechanism, but also you have this liquid chemical known as a poison which can be released in a moderator and stop the reaction. What separates these two tubes is an annulus gap, which is around 6 millimeters long. So these tubes are relatively held closely together. And what's interesting is that a gas is flowing between the gap separating these two tubes. The annulus gas system, which flows between these two tubes, is a monitoring mechanism for that of the pressure tubes. It's monitoring for changes in moisture. Remember, these reactors are being monitored by operators at all times to make sure they're running safely. Fuel plays a really important part in the CANDU reactor, and the reason why is because without fuel, you don't have a source of heat which is used to ultimately spin those turbines and create electricity. Well, I got a really cool surprise for you, but first and foremost, make sure you don't tell anyone how I got one of these, which is a fuel bundle. Yes, this is a bundle that's used in a CANDU reactor. And yes, it's not the actual bundle, it is a replica, but it looks exactly like this. It's the same size, it's the same dimensions, but I wanna thank someone. I wanna thank CAMCO, which is an organization which actually manufactures these fuel bundles, for letting me borrow this as an educational resource. Thank you. This is an empty fuel bundle, by the way, but it's the size of a wooden log. Also produces millions of times more energy than a wooden log, surprisingly. It also spends around 12 to 18 months within a CANDU reactor. Yeah, nuclear fuel lasts a very long time because it's energy dense. And also nuclear fuel releases a lot of energy slowly over time. Sometimes nuclear energy is conflated with nuclear weapons, and it's very different because nuclear weapons release that energy instantaneously, whereas nuclear power reactors are really harnessing that energy. It's kind of like the difference between a gun and like that of a furnace, or a car, which is using a combustion reaction for productive purposes. An interesting fact is that you can actually hold a fresh fuel bundle in your hands safely, and I'll explain a little bit more as to why. But these fuel bundles, the fresh bundles, are held using cotton gloves. And the reason why is because you don't want the oils from your hands to go onto this fuel bundle before it's pushed into the reactor. The reason why it's safe to hold a fresh fuel bundle before it goes into a CANDU reactor is because this fuel is made out of natural uranium. Yes, it's made made out of a rock that's mined and processed into ceramic pellets and ultimately pushed and wrapped up in this bundle. And natural uranium is slightly radioactive, and so are bananas. They're both safe to hold in your hands, especially when they're fresh. All right, let's chat a little bit more about the fuel bundle and its design. Well, starting off with the natural uranium. Now, natural uranium is found in a rock. Yes, uranium is a rock. It's naturally radioactive and found across the world, usually in places like Saskatchewan and Canada, but also sourced in places like Kazakhstan, and also Australia has some reserves as well. However, this fuel is mined, it's taken out of the earth, it's processed, and it's also shaped into hardened ceramic pellets. These pellets are around the size of a quarter, so around this big, and those are loaded into these fuel bundles. The reason why nuclear fuel is a ceramic is because ceramics are heat resistant. Yes, they can handle a lot of heat. Now imagine your plates or trays that are made out of a ceramic. You can place them in the oven, you can place them in the microwave, and they are heat resistant. They'll last you several years. So same principle applies to that of nuclear fuel. And what's also interesting is that these pellets lock in any fission products that are produced from a nuclear chain reaction. So they also act as a containment method. And these fuel pellets are contained inside of these zirconium alloy sheath. Okay, so imagine like a sword has its sheath. So this is the sheath, and it's also another containment method which holds these fuel pellets, and it's sealed. So as you can see, this is welded together pretty damn well, right? So maybe I'll have some cool B-roll which shows you the sealing of this bundle, all right? Also, what's interesting is that each of these pellets weighs around 20 grams. Yes, so it's the size equivalent to that of a quarter, but the energy density is immense. It has an energy equivalent to that of 400 kilograms of coal, and also that of 410 liters of oil. So imagine 20-gram fuel pellet is equivalent to 400 kilograms of coal energy, which is incredible. Each of these bundles has around 1,110 fuel pellets. And as you can imagine, that's a lot of energy. In total, the bundle itself weighs around 22 kilograms. So imagine if a pellet has the same energy density or energy equivalent to that of 400 kilograms of coal, each bundle has the energy equivalent of around 3.5 rail cart loads of coal. Yes, 3.5 rail cart loads of coal is around 440 tons of coal. Yes, something that can fit into my hands has the energy equivalent 440 tons of coal. The fuel bundle is actually a perfect weight for bicep curls. Yes, I think 60 pounds is perfect for a nice workout session. The materials used to construct a nuclear reactor directly impacts how efficiently a nuclear reactor operates. Think of it like a Tesla Model S. Tesla uses a lot of aluminum in its vehicles, and the reason why is because aluminum is light and it helps the car achieve a better fuel economy. Reactors are no different. So in a CANDU, the aluminum equivalent is that of zirconium or zirc alloy. Zirconium or zirc alloy is used throughout the CANDU nuclear reactor. And the reason why is because this metal is invisible to neutrons. Yes, neutrons, the spark that initiate the nuclear chain reaction, can easily pass through this material. Also, it's corrosion resistant and it's also heat resistant. It has the perfect properties for a nuclear reactor. The benefits of neutron economy is such that you get more energy out of the fuel that you're using, which means less operational costs and cheaper electricity. Fun fact, the ring that I got from graduating from the nuclear engineering undergrad program is actually made out of zirconium metal. And you notice that this metal is slightly darker, and the reason why is because it does have the ability to oxidize a bit and turns a little bit darker. And you notice that this other ring that I'm wearing, the stainless steel iron ring, is a lot shinier than that of the zirconium ring. And also in the CANDU reactor, zirconium makes up the fuel bundle sheath. So the sheath for fuel bundles are actually made out of zirconium. The pressure tubes are also made out of zirconium, and there are many other important parts within a CANDU reactor that are made out of this alloy. Let's chat more about the life of a fuel bundle in a CANDU reactor. So the fuel bundle, like I said, starts off fresh with cotton white gloves and loaded into a fueling machine. Now this fueling machine is a robotic arm which inserts the bundle into the reactor while it's operating. Now this bundle, depending on the location within the CANDU reactor, lasts around 12 to 18 months in the reactor. All right, so over time, over this 12 to 18 months, these bundles are releasing energy, all right? And this energy in the form of heat is used to heat water. Now in the background, there are teams of engineers and physicists that are doing various calculations of fuel bundle efficiencies, and also to understand when these fuel bundles are spent. Now, once these fuel bundles are used up, it becomes spent fuel, and they are simply removed from robotic arms which pull out these fuel bundles and send them off to be stored in a fuel bay. A fuel bay is a large pool of water which holds all of the spent fuel from a nuclear reactor. Like I said before, these fuel bays are large pools of water. They're also leak tight, they're double concrete walled, and also they're resistant to natural disasters like that of earthquakes as well. They're very safe and they're safely store all of the spent fuel in the lifetime of a reactor. Why is spent fuel stored in large pools of water? The reason is simple, and the reason is because these large pools of water remove any residual heat that's coming off of the spent fuel. So over time, these bundles are still producing heat after they're removed from the reactor. And what these pools do is they take out this residual heat over time. What's interesting is that you can safely walk on top of these fuel bays without having to worry about any radiation harming you. And the reason why is because the water does such a good job in protecting you from the radiation that's produced from the spent fuel. While spent fuel is stored in these fuel bays, it's cooled through circulating water through heat exchangers. Also, water is continually filtered out through different mechanisms like filters and also ion exchange resins. Fun fact, you'll notice that these fuel bays glow a little bit blue, kind of like the light that I have back there. And the reason why is because of a phenomenon called the Cherenkov effect. This effect is created when charged particles within these fuel bundles moves faster than the speed of light while in water. The energy radiates as blue because of the disruptions created by radiation, which create shorter wavelengths. It's basically the water version of a sonic boom. What happens to the spent fuel next? Well, what happens is after spending years inside of these fuel bays, spent fuel is next transferred to large concrete storage containers. The advantage of putting spent fuel in these storage containers is because it minimizes the amount of filters that are used in the fuel bays. It also reduces operational costs and maintenance. And also, lastly, it reduces the chances of corrosion taking place in the fuel sheets. Lastly, the fuel is then taken out of these storage containers, where the fuel is then sent off to deep geological repositories, or called DGRs, where the fuel is encased in specially designed canisters and then bentonite clay. This permanent disposal method of deep geological depositories is a very safe disposal method for spent fuel, and I'll be describing this a little bit more in another video. Let's get down to the basics. Why do CANDU reactors use natural uranium instead of enriched uranium, which most power reactors across the world use? For those that don't know, enrichment is when you take uranium and increase the amount of U-235, which is the fissile isotope, the most important isotope that does a lot of the legwork in the uranium. So think of enriched cereals, which have more protein, right? So protein used to build muscles, very important. So enrichment is very similar. It increases the power output and the longevity of the fuel while it's in a reactor. So why is CANDU using natural uranium? Well, let's start by explaining the science of the different isotopes within uranium and how they play important roles within power technologies. The two naturally occurring isotopes within uranium are U-235 and U-238. U-235 is, think of it like yang energy, fire energy. It does a lot of the legwork. It starts the reaction. And second is U-238. So it's very important as well. Think of yin energy. Think of water, fertile. It eventually becomes yang energy. So those two are very important in nuclear power reactors. U-235 is active, and that's why I named it as yang energy, that fire energy. It emits neutrons, and without it, you can't facilitate a nuclear chain reaction. What's interesting about U-235 is that it only encompasses 0.7% of all uranium on Earth, so it's very, very rare. Next is U-238, which is fertile, and by itself, it can't do much, but think of it like a seed. By itself, it can't do much, but once it's activated, it can produce a lot of energy. Most conventional power reactors across the world, like pressurized water reactors or boiling water reactors, use enriched uraniums enriched to around 3 to 5% U-235. So centrifuge technologies take U-235 and increase that amount from 0.7, which is the naturally occurring state, to that of 3 to 5%. CANDU reactors, on the other hand, are able to use natural uranium at 0.7% U-235. And the reason why is because of its heavy water moderator. Now, the heavy water moderator, like I said, is very different from light water moderator that most conventional reactors use. Heavy water moderators have the ability of increasing the neutron economy of a nuclear chain reaction. Let's start with the basics. What is a moderator? Now, a moderator is a fancy way of saying controlling. Moderating a reaction is controlling a reaction. Heavy water, or at times called D2O, is the moderator in a CANDU reactor. Heavy water is unique in such that it has an extra neutron, and because of this, it decreases the ability for it to absorb neutrons. And remember, neutrons are like the sparks that ignite a nuclear chain reaction. The more neutrons you have floating around in the moderator, the more efficient your reaction. Since heavy water is such an efficient moderator, you can pair it up with naturally occurring uranium. And this is great because you don't need to enrich the fuels, which is an expensive process. However, you do need to enrich the water. Heavy water needs to be created, and it is quite a bit of an expensive process to create. Interestingly, historically, there were around 3 different approaches when it came to choice of moderator for nuclear power reactors. And number one was graphite. Graphite was used by the UK and the Soviet Union in different reactor designs like the Magnox and also the RBMK reactor. Then there was light water, which was used by the United States, who chose to invest rather in enrichment technologies. So this was another interesting design choice when they designed the BWRs and the PWRs, pressurized water reactor and boiling water reactors. These are now the most popular reactor types across the world. And lastly, Canada had a lot of experience when it came to heavy water, and thus it chose heavy water as a moderator for its CANDU reactor design. What are the benefits of using natural uranium as fuel for the CANDU reactor? Well, simply, you don't need enrichment facilities, which also takes out the proliferation concern. Also, the fuel is relatively cheap. However, the heavy water moderator is expensive. A relatively unknown fact about the CANDU reactor is that it can use spent fuel from light water reactors. Yes, the CANDU reactor can be used as a waste burner. This fuel is called DUPIC or DUPIC, direct use of pressurized water reactor fuel in CANDU. Pressurized water reactors are the most popular reactor types across the world, and their spent fuel can be used directly in a CANDU. The reason why is simple. It's because of the high neutron economy from the heavy water moderator. This way you can drastically decrease the spent fuel usage from not only pressurized water reactors, but also CANDU reactors. CANDUs can also use MOX fuel, which is another recycled fuel type, so it can be used in a CANDU reactor. And with modifications, the CANDU can also use thorium fuel blends within the reactor. Another really cool feature about CANDU reactors is that they can be refueled while operating. This is really unique because other conventional nuclear reactor types like the PWR and the BWR need to be completely shut down before fuel can be exchanged. CANDU reactors, on the other hand, are equipped with robotic machines which push in fresh fuel and pull out spent fuel while the reactor is operating. And this has a lot of benefits. This feature is called on-power fueling, and on-power fueling has a lot of interesting benefits, one of which is maintaining reactor flux across the reactor. So as the reactor is operating, you can optimize location of certain fuel bundles. So you can insert spent fuel in specific locations in order to have optimal burnup. Burnup is the efficiency of drawing out energy from the fuel bundles, and on-power fueling facilitates that. Another benefit of on-power refueling in a CANDU is that a CANDU reactor can operate for years at a time without having to be shut down. And this is why CANDU reactors have broken world records again and again for being able to operate for long periods of time. I think the longest period of time that CANDU has operated for is more than 3 years consecutively. This is incredible. This is great for maintaining grid stability. You have a reliable amount of electricity that's being provided for years on end without having to be shut down for fueling outage or for maintenance. This is incredible. All right, so let's chat a little bit about reactor safety systems. And in a CANDU reactor, safety is #1 priority. There are several safety systems within a CANDU, and it would take me around 5-hour video for me to cover all of them, but I'm gonna cover some of them in a very high level. Well, let's start off with the very first system, which is control rods. If you wanna shut down a CANDU reactor and you wanna do it fast, you deploy this first safety system, which is control rods that shut down the reactor. So if anything irregular is detected within a CANDU, you've got 28 shutdown rods that are on hot standby to be dropped right away into the reactor core. And this shuts down the reactor within seconds. What's interesting about this feature is that these rods are gravity drop, and they're also spring assisted to give it that little bit of an extra push. These control rods are made out of a metal called cadmium wrapped in stainless steel. And what's interesting about cadmium is that it's a metal that's great at absorbing neutrons. Remember, neutrons are those sparks or those bullets that start the fission reaction and maintain that reaction. And what's great about cadmium is that it absorbs all of these neutrons, stopping the reaction at its core. A secondary shutdown system, which is completely different from control rods, is called the chemical poison. Poison because when you poison the reactor, it kills a reaction. It's a chemical agent which is released into the reactor core through various pumps. And this chemical is called gadolinium nitrate. It does the same thing as cadmium. It absorbs neutrons. So there you have it. You have both a physical system and also a chemical system which can be deployed independently to shut down a CANDU reactor. Let's talk about some of the other safety system in the CANDU, which is the first starting with ECI, which is emergency coolant injection. In the unlikely case of a pipe break or any other disturbance, there are large reserves of water set on standby to inject water right into the core of the reactor, and this keeps the fuel bundles cool. Pressurized nitrogen tanks and also pumps keep that water circulating. All plants have around 2 or 3 injection systems, and in case of a pipe break, the reactor buildings have a circulation system which have a collection basin and then recirculates the water back into the core in order to cool the bundles. Let's talk about backup power generators. The way a nuclear power reactor works is that it's producing electricity, but it's also consuming electricity from a grid. And in case of a blackout or outage, there are safety systems that have been put in place in order for the plant to keep operating. There are 4 4 independent backup power systems in a CANDU reactor. The first is on-site power. And like I said before, the nuclear power plant is producing electricity, and that electricity is used to operate pumps circulating water in the reactor. Number 2 is backup diesel generators. These are massive generators which are independently fueled by diesel on site. And if there is a blackout or any disturbance, these diesel generators are turned on and can operate pumps to cool the reactor down. Number 3 is emergency power generators, and also number 4 are emergency batteries. Besides these active safety systems which are built into the CANDU, there are many other passive safety systems that you can find in a CANDU reactor, which are physical containment barriers. Let's start with number 1 is the fuel pellet itself is designed so that it traps all fission products that are produced from the reaction. This is one source of containment in a CANDU reactor. Number 2 is the heat transport system. So the heat transport system is independent from that of the secondary system, which produces steam that spins turbines. And this is the separation in a nuclear reactor from the nuclear side to the non-nuclear side is also a containment barrier. Remember, nuclear plants, the condenser systems are being cooled by lake water, and this side of the reactor is not contaminated. It has nothing to do with the nuclear side. The nuclear side is safely contained, and the primary heat transport, the system which connects the reactor core to the steam generators, is an independent system. So this is another physical containment barrier. Number 3 is a hardened concrete vault that surrounds the reactor core. All right, so other than those large domes that you see called the reactor buildings, there is another containment barrier known as a vault. Okay, so this vault is made out of heavy concrete and is placed right outside of the reactor core. Last but not least, the most important is the RB, or the reactor building. And you'll notice that CANDUs and most other reactors across the world have these dome-shaped concrete structures which encapsulate each and every single unit. What's interesting about these reactor buildings are made up of 1 meter long reinforced concrete. They're some of the hardest materials on the planet. These reactor buildings are specifically designed for emergency situations and also for any potential steam release that may come out of a reactor. Remember, reactors don't blow up, okay? That's not how nuclear power plants operate. They're not weapons. Rather, they're usually steam that's released from a reactor unit. Also, multi-unit CANDU reactors have the reactor buildings which are connected to a vacuum building. So a centralized vacuum building is really cool because what it does is if there's any situation that takes place in any of the units, that vacuum building sucks up all the steam that's produced. So there you have it. Really appreciate you watching this video. Hope you get a chance to check out maybe my simplified version of the CANDU reactor if you're more interested in a 5-minute overview of the CANDU. Till then, hope you enjoyed this video. Take care. Thanks for watching. Bye.